So we are going to continue the discussions of quantum spin systems and phase transitions. I have here put a new address for the lecture notes. The address I gave you yesterday is valid. This one is going to be more permanent. So you can, write it if you wish. I'd like also to thank Christian Heinzel. Yes? It's 13. Because we are in 2013, sorry. Thanks. So I'd like to thank Christian Heinzel for inviting me last year in Tübingen, where I discussed a lot of those ideas. So I benefited a lot of the feedback from all the crowd of Tübingen. And the lecture notes actually were those I wrote also back then. So what I'd like to start with is something that we saw yesterday, which is this amazing formula for going from the microscopic world to the macroscopic world, so the formula for the free energy. So you remember that it takes the following shape. We define this function of f, beta h, which is like the limit in the as the size of the system becomes over beta lambda, the trace of exponential minus beta and the Hamiltonian. I don't know. Yes, h lambda. So I like just to point out a curious anecdote in the history of physics and statistical mechanics, which is that it took a while for this notion of infinite volume limit to be accepted. And there is this story about the conference in the centenary, in honor of the centenary of Van der Waals, which was held in Amsterdam in 1937. And over there, Max Born was presenting Mayer's theory for statistical mechanics to the audience. And basically, the starting point was the partition function for a classical gas, where you integrate over all positions and velocities of particles. And the question was whether such formula was describing all possible phases of a system. And some people objected strongly. One among them was Arnold Sommerfeld, who said that if you have several phases, you should have different descriptions, and then you look at the equations of continuity, and that's the proper way of doing it. Other people, like Van der Waals Jr., said that no, the partition function contains all possible information of a system, and everything should be there. But then if you want to get something like discontinuities associated to phase transitions, you need to take the thermodynamic limit, because otherwise all the equations you write are obviously analytic. So then apparently there was no consensus reached during this debate. So the chairman, who was Hendrik Kramers, decided to have to make a decision with a vote. So people voted, and we were lucky. We all are lucky. The thermodynamic limit won narrowly. So this formula stands. Yes? Sorry? Isn't there what? Oh yes, a log. Thank you. Here. And minus sign indeed. Thanks. Right. So I'm sure they voted on the right formula. Otherwise, okay. So today I'd like to discuss the beautiful proof for the existence of phase transition due to Dyson, Lieb, and Simon for the quantum Heisenberg antiferromagnet, and it mirrors the proof we saw yesterday for the classical ferromagnet of Friedrich Simon Spencer. So let me remind you of the setting, or introduce the setting for this case. So first we have a graph, and the graph is going to be, as yesterday, something very regular, like minus L over 2 plus 1, up to L over 2 to the power D. So it's a box of size L, which we label like that. L is always going to be even, and E, the set of nearest neighbors with periodic boundary conditions. It's again going to be essential in the proof, even though it should not for the result. Then we take the Hilbert space to be the tensor product over all sides of a lattice of C2S plus 1. So we consider the model with general spin S. And the Hamiltonian, let me recall what it is. It's the same as what we considered yesterday. H lambda H with parameter U is this asymmetric Heisenberg, so -2 sum over pairs of nearest neighbors, or xy subsets xy in a set of edges E, and then Sx1 Sy1 plus U Sx2 Sy2 plus Sx3 Sy3 and minus H sum of Sx3. So again, it describes those spins in an external magnetic field in the direction 3. And as yesterday, we also need the dual lattice in the sense of Fourier theory. Let me still write this down here, then I can keep it for a while. So lambda star is going to be 2 pi over L, and then minus L over 2 plus 1, up to L over 2, to the power D. And we also need the dispersion relation of the lattice, epsilon k I equals 1 to D, and I think I have 2 also, yes, of 1 minus cosine ki. It's important to remember that epsilon k behaves like k square around k equals 0. And indeed, for long wavelengths, one expects the lattice not to play a role, so it should be like in the continuum. So, yes, so the question is about the U, so it breaks the continuous symmetry. Yes, that's actually very important. We plan to have, I mean, it has to be that the long range order happens in the 1-3 plane. So this is completely correct. I know that's not exactly the standard notation, but usually what happens is that the U is put over here, and using reflection positivity, one proves magnetization in the 1-2 plane. And it's actually much more natural to look at it this way. So the theorem, let me state the theorem of Dyson-Lipps-Simon, which is 3-1 in the notes. So Dyson-Lipps-Simon 78. And so we assume H equals 0, which has to be L even turns out to be essential for the proof. And another essential thing for the proof is that the parameter U belongs to the interval -1 to 0. So it corresponds to the antiferromagnet. I mean, -1 is the antiferromagnet, 0 is the XY model. And what should be the simpler situation of the ferromagnet turns out not to be treated by this theorem, nor by any other theorem, actually. So then, the claim is that we get the lower bound for the sum of correlation function. So you remember this thing we considered yesterday, which is something like the Chesaro average of the correlation function. I'm not going to introduce, but this brackets means the expectation of those operators in the quantum state. So 1 over partial function trace of this exponential minus beta h. And the goal is to show that this does not decay to 0, and the Chesaro, I mean, this Chesaro average is larger or equal than, and the lower bound is 1/3 SS plus 1, this spin operator, sorry, spin value, which is half integer, minus, and then comes 1 over square root 2, the size of the domain, sum over case in lambda star without 0. And then you have a ratio of epsilon uk over epsilon k. I'll write in a minute what this is, and still minus something which is, equal to 1 over 2 beta lambda sum over k in lambda star without 0, and 1 over epsilon k. And where this function epsilon k, u of k, depends on u, is like the sum I equals 1 to the dimension d, 1 minus cosine ki. I hope I'm not I think there should be a u over here. It's not in my notes, but I'm pretty sure that there is one. Well, so sorry, I have a little bit of doubt over here, but it's not going to change the arguments. And then we have the expectation of S0, 1, S1, 1. So this is the correlation function between the origin and the neighbor in the direction 1. And because of translation variance and rotation variance, actually any pair would work here. And it's not over, plus u minus cosine ki. Oh, actually, here there is a u. So my suspicion is that this should be like 1 minus u cosine ki. I'm pretty sure it's correct in the notes. I probably just copied badly yesterday. And then we still have this correlation function S0, SE1 in the direction 2. So Simon, one observation is that it's easy to bound all those terms, and a bound is that this is less or equals than SS plus 1. So let's see what we learned from this. Of course, we would like the right side, the lower bound, to be strictly positive at a large enough temperature. So here, if you're in dimension 3 and more, this is integrable. So you can take the infinite volume limit, you'll get the integral of 1 over epsilon k. It behaves like 1 over k square on 0, that's integrable. And you have a 1 over beta, so you can make this as small as you want. That's not a problem. What is new compared to the classical case is this term over here. But if you look at the value of a spin, capital S, this is smaller than SS plus 1. So for S large, this behaves like S on this part, while this grows like S square. So the result definitely is strictly positive for S large enough. And then the question is, to get explicit conditions about which values of S are allowed, which dimensions are allowed, and then one can look exactly at what's proved. So the fact is that for the Heisenberg model with spin 1/2, the result holds for all dimensions 3 and more, not quite this lower bound, but another lower bound by Kennedy-Lipschastri a bit later. And actually it covers all the cases except the ground state of the antiferromagnetic Heisenberg model in dimension 2, which the ground state is still, one can still do something. So anyway, so in this lecture, and yes, Thomas? That's E1. But you can put EI, doesn't matter which direction you choose. Yes? Okay, so this is the result. And I'm going to describe the structure of the proof, and then we'll review it. That's the goal of this hour. So the proof is more difficult, and let me comment on this. More difficult than in classical case. And the main reason is that the usual infrared bound, the infrared bound for the usual correlation function does not hold. So because the infrared bound, so if it's like the classical case, we would expect something like that. Take S0 free, Sx free. This is a function of x. You take the Fourier transform of this function at k. And this you would like that this is less or equals than 1 over beta epsilon k. Actually, if it's not beta, but any function which diverges with beta, this would be fine. But one can show that this cannot be true. So, cannot be true. So look at the notes for saying the argument which was already in Dyson-Lip-Simon. So what the whole is another infrared bound, but not for this correlation function, but for the Duhamel two-point function. So one looks at something like that, S03, Sx3. And so this is less or equals than 1 over, as it turns out, there is a 2, but does not really matter. Actually, no, it does. 1 over 2 beta epsilon k. And what is this object over here? This is Duhamel, or Duhamel inner product. And where the inner product between two operators A and B is defined as 1 over z, the integral from 0 to beta ds, and then the trace of A exponential minus sh, B exponential minus beta minus sh. So if you do not play with this integral over here, but you just you take B over here, then you get the usual two-point function. I'm also not sure. I have a hesitation. Probably I would like to put a beta over here. Sorry? No, it does not. Oh, sorry. Here, Fourier transform of this thing. Thank you. Yeah. This correlation function with S0, S3 defined like that. And still, so it's a function of x, you Fourier transform, and then you get the upper bound. But then you cannot do the argument as before, where you remember that it was crucial that that we looked at the value of the correlation function at 0, something like that. And this had to be a constant. So it was 1/3 for the classical model. When you look at the Duhamel two-point function, you don't have an obvious lower bound for this thing. So then the proof goes a bit differently. And it still relies on on getting an infrared bound for the usual two-point function. So let me give you the structure of the proof. Which is similar to what we saw before. So we start by proving reflection positivity. And this will be the beginning. This places a lot of restrictions on which setting we have. And in particular, this requires u less or equals to 0. This is where the restriction is. Once you have reflection positivity, there will be this Gaussian domination property. So we will again introduce some partition function with external fields, and it has to be maximized at 0. Then this, once you have Gaussian bound, but for the Duhamel two-point function. So exactly the one which is written over there. So this follows from the Gaussian domination. But then it is transferred as an infrared bound, which is more complicated. I mean, it has an extra term for the usual correlation function. And this is done using an inequality actually reinvented by Dyson-Lip-Simon, but it was originally proved by Falkenbruch. So then you get another infrared bound for the correlation function, and from this you get long-range order, exactly like in the classical case, just by using properties of Fourier transforms and inverse Fourier transforms. So now I'd like to describe the steps. I'll be quite fast for the beginning, but the notes are self-contained, and I mean they contain everything. But here, the goal is really to finish in 1 hour, so it's just for orientation. So let me describe reflection positivity for quantum systems. Maybe let me put a 1 over here. So let me give you a lemma. 3.2. I mean, we have this domain, which is a nice box. A rectangle would be okay, but let's restrict to a box. And we'll get a reflection planes across edges, so that the domain lambda is split into 2 parts, lambda 1, lambda 2. This is very similar to the classical case. And then in the classical case, we had the variables of spins on the left, those on the right. Here, what happens is that the Hilbert space for the whole domain has the structure of the Hilbert space only for lambda 1, tensored with the Hilbert space on lambda 2. And then a part of the structure is the same. There will be operators acting on the left, operators on the right, and operators coupling the 2 parts. So this is what is similar to the classical case. But of course, we are discussing now operators, and the reflection positivity property needs to be extended. So the abstract property can be formulated like that. Assume that some Hilbert space has the structure a smaller Hilbert space, so this should be a calligraphic little h, tensored with another copy of itself. And we are given operators A, or matrices. I should say that we assume finite dimensionality. We are given A, B, C, I, DIs to be matrices. Ci means we have C1 up to Ck. So matrices in the smaller Hilbert space, little h. So then the claim is as follows. It's a long inequality actually. So we take the trace in the big Hilbert space. There is an absolute value. And then the trace is going to be of an operator which is like capital A tensored with identity on the other part, plus identity tensored with B, and plus, or actually minus the sum I goes from 1 to K. K is an arbitrary finite number. And then the coupling will take the form of Ci tensored with identity minus identity tensored with Di, everything to the square. So the square means actually only the diagonal part really matters, and it will be of the form Ci times Di, exactly like we expect. We will have a spin operator over here, spin operator over there. So that's the trace of this. I mean, this is the object, and this is less or equal than when we take somehow all the things on the left and reflect, and all the things on the right and reflect. I should say that there is a square over here. So this is less or equal than h, and I suppose I need absolute values. Exponential of A tensored with ID plus, now ID tensored with A, actually it's not quite A which comes in, but A bar. And it's not A star. I'm going to tell you what A bar is. Minus the sum I run from 1 to D, and then Ci tensored to ID minus identity tensored with Ci bar to the square. And then the trace, and then what you get is exponential of this time B bar tensored with ID plus ID tensored with B minus the sum, and then you get what you expect, di bar, tensor id, minus id times d bar. I'm not going to put it. So this is this reflection positivity lemma. And it's very important to understand what those operators bars are. So where a bar is the complex conjugate of A with respect to some basis. So you choose one basis when you have your matrix written in terms of matrix elements. And the bar means just that you take the complex conjugate of every number, but without the transposition operation. And there is a good reason for it. You use some Cauchy-Schwarz at some point, I mean some Trotter formula to get a long product. I think you also decouple these things using external fields, and then it's a Cauchy-Schwarz inequality. Then you get a lot of, a large expansion on the right side, and you like to rearrange them like that. And it's very important that the product of operators retain its orders. Now, when you take Cauchy-Schwarz, normally you take an absolute value, and it's going, the absolute value of a trace of operators gives you the trace of the adjoints, but in reverse order, and that would not work. But if you take those complex conjugates, they maintain their orders. So that's why it's very important in this inequality. So this is a lemma. I'm not going to prove it here. So next we are going to exploit this lemma. So let me arrange those boards. Here I can already gain some. Are we getting something? Yes, we do. And I can still move this one up. This one up a bit. So the second part is to introduce this partition function with fields and to get the so-called Gaussian domination inequality. And so let me introduce the notation. So the fields will be, as yesterday, denoted by V. Some people must have guessed why a field is denoted by V. I guess all the German-speaking people would know. And H, I guess it's Feld, or no, it's F. Actually, I don't know why people used V. So, you assumed. All right, so I betrayed my absolute knowledge of German. So, and H equals delta V. So here we have a local magnetic field, which is going to be given by the discrete Laplacian acting on the fields V. Delta is the discrete Laplacian, we saw it yesterday. And then the Hamiltonian H of V. By the way, I forgot to say, Vx are real fields. Each Vx is a real number. And H of V is going to be like H lambda 0 U, so the Hamiltonian with zero magnetic field, minus the sum Hx Sx3. Actually, I could have put the H over here, but it has to be understood that now the external magnetic field depends on the location. And we have a partition function Z of V in the big Hilbert space of exponential minus beta H lambda, H of V. I'm also going to use another partition function, Z prime, which is like Z of V, but with a correction over here. Exponential of 1/4 beta, and then the inner product between V and delta V. This is the inner product in lambda, so the sum over X of Vx bar delta V at X. So the thing is that this is a more natural objects to work on. That's the objects where the Gaussian domination property is stated. So lemma for this subsection, which is that if u is less or equals to 0, then for any reflection R across edges, so exactly like the picture over there, through any any edges, but in all possible direction too, we have that if you take z prime of v1, v2, so this is the partition function z prime, where you have the fields on the left part of the reflection plane, the fields on the right part. Take this to the square, and this is less or equals than v1 reflected part of v1, z prime, the reflection of v2, v2. So this is you get reflection positivity. And then once you have this, you immediately have for consequences the Gaussian domination property. So consequences z prime of v is less or equals than z prime of 0 for every real fields v. And the proof starting from here and getting here is exactly the one we saw yesterday. Just this clever trick of considering a maximizer, and then you get maximizers which are more and more identical by looking at all possible reflections. So this part is the same. I'm not going to do it. And then I'm just going to comment that the proof of lemma 3.3 follows from lemma 3.2. It's not totally obvious, but it's a bit, now that you have lemma 3.2 and you remember what we did for the classical systems, it mirrors it. And the idea is that this thing, with z prime v1, v2, and given the reflection plane, you write it as everything on the left, everything on the right for the coupling. And you apply then this inequality. Now the difficulty is to recognize that what you have on the right side is exactly the partition function z prime of v1 r of v1. So since you go from A cross ID and the A contains the v1s, you reflect and you'll get the reflection of the v1s. One tricky aspect is that you get all those complex conjugates A bar. The idea is to apply this inequality where all the A's have the real coefficients. Then A bar is equal to A, and indeed what you get on the right is exactly the partition function with the reflection fields. So it requires all operators to satisfy A bar equals A, which means that all coefficients have to be real. So now what about those spin operators that we have? In the usual basis, S1 has real coefficients, S3 has real coefficients, and S2 has purely imaginary coefficients. Now you can check because of parameter u that we have over here. This you can also write as the square root of u over here, square root of u over there. So what you're dealing with is the matrix square root u times S2x. And the combination is, again, purely real. So this is where the restriction of u being negative comes from. And this looks like technical. Anybody who has a good idea to go over this is very welcome, and it would be a major advance which has escaped people for already 40 years, I guess, soon. Yes? Yes, indeed. But I haven't completely understood this, because then you have further work by Froelich, Israel, Lieb, Simon, formulating the reflection positivity in a more abstract fashion. And then Speer indeed proved that, or Speer proved that the Heisenberg ferromagnet cannot satisfy this. But does it completely rule out any possible reflection positivity technique? I've never quite understood this. Because, you know, one does not need completely everything. For instance, one needs these Gaussian dominations only in the neighborhood of 0. So if you don't have quite this for all V, but only for V close enough to 0, that's enough to continue. And also, this reflection positivity using fields, it's not exactly the abstract reflection positivity in Froelich, Israel, Lieb, Simon. It's very closely related, but I've never completely understood the connections. So I'm a bit embarrassed. I'm not sure whether the objection of Speer, which is definitely a very interesting argument, completely rules this out for the Heisenberg ferromagnet. Or for instance, what would happen if U is extremely small but positive? So, because this is also something which is not totally clear to me. One would expect that if U is tiny, that maybe still, because you gain from the other parts of the operators, you could still do it. But it is, so it's something which, yes, I mean, there are still plenty of open questions. Certainly, when U is negative, everything goes through. That's actually the main message. I mean, we do get a wonderful result out of all this. So the next step is a very technical one, which is that once you have this property over here, which means that you can get a corresponding inequality for this object. So this is Gaussian domination. Then it implies the infrared bound for Duhamel. And let me just write down, well, just a few equations, but not much. I mean, the idea is to apply the inequality where Vx is, like we saw yesterday, some tiny number eta cosine kx. So you fix k, and this is a function of x you consider. Inequality, expand to lowest non-trivial order of eta, which is eta square. And in order to have a maximum at 0, you need that the second derivative be negative. And this gives you the right property. Let me maybe just point out that you would expand z of v, and it would give you something like z of 0. The linear terms disappear, plus 1/2, and then you have an inner product between, I mean, on lambda, h, which is the Laplacian of v, and then the second derivative of zv by dhx dhy h plus O of eta 4. And let me remind you what is h. So h equals delta v. But when you take v like that, then this is an eigenvalue of the discrete Laplacian. So you also get minus epsilon k times v. So h is actually just proportional to v. So you have some expansion like that. And if you look at what you get out of the second derivative, that's the Duhamel two-point function. That's why you get this. And because you have still a sum of this h and they are cosine kx, what you get is the Fourier transform by rearranging and using lattice symmetries. So you get the Fourier transform of the Duhamel two-point function. That's exactly like the classical case. Some careful checking, and I urge everybody to do it. So at this stage, eventually we get that if you take the Duhamel two-point function, its Fourier transform at k is less or equals than 1 over 2 beta epsilon k. Next step is what to do with that, and this is going to be this Falk-Bruch inequality. Thomas? The h is proportional to v, which is proportional to eta. So this is like eta square. Well, so the inequality. So this is the inequality over here, and you can immediately write down the inequality for the zv. So it's going to be like zv times this is less than z0. So next step is Falk-Bruch, and this is a kind of nice little algebra that I'd like to do a little bit in more details. So Duhamel function and Falk-Bruch. Falk-Bruch inequality, say. And so the goal is to show that if you have such an inequality function S03 times Sx3, well, it's Fourier transform, then it should satisfy some infrared bound, so some bound which depends on k. And let's discuss the setting a bit. And we can introduce something which can be called Duhamel inner product, which is that you take two operators, A, B, and the inner product is going to be given by 1 over the trace of exponential minus h. So we are given some Hilbert space, which is going to be finite dimensional here, and some Hermitian matrix H. And then for any matrices A and B, we get 1 over trace of exponential minus h. The integral from 0 to 1 ds, the trace of exponential minus 1 minus s h, yes, a star, exponential minus sh b. So we define this object over here. It can be checked that this is indeed an inner product, which is antilinear with respect to its first component and linear to its second. Then we can get some properties. So let's define the function f of s for given operators, given an operator A. Suppose you take the trace of exponential minus 1 minus s h sh a. So one can check, and it's not too hard to see, that this is positive. If you don't see it, the idea is just to say that this is like the trace of exponential minus 1 minus s over 2 h, a star, here minus exponential minus s over 2h, exponential minus s over 2h, a, and then the remaining part I put on the right side by cyclicity, exponential minus 1 minus s over 2h. And if you call this b, then this is a b star. So here, that's not hard, but it's a good trick, and one gets that this function is positive, and it also shows that the inner product, if you take two, satisfies the positivity property. Next, so let me maybe move the last one up and the other down. Actually, it's easier to do it this way once it's... Okay. So the next thing is to check that the second derivative, this function f of s is positive, but it's also convex. And the reason is that you can check the second derivative respect to s, and what you get is the trace exponential minus 1 minus sh. And then when you differentiate, you bring down the h in different ways. So you'll get ah star exponential minus sh, and then ah like that. So we get something similar to before, but now we have a commutator over here. So this is, of course, larger or equal to 0 by the same argument before. So this function is convex, and then we get immediately a nice inequality, which relates the usual two-point function and the Duhamel two-point function. So the inequality is like that: 1/2, and then we don't know whether A is Hermitian, so let's take A star. And this, so this is essentially like the inner product, sorry, the correlation between A star and A. This bracket means trace of this object, exponential minus beta h, everything divided by the partition function. So this, when you look at it, it's like 1/2 and 1 over the trace exponential minus h, and then you get f of 0 plus f of 1. So, I mean, if you put f of 0, then you get exactly trace of this, I mean, exponential minus h, a star b. So, but then, I mean, we average the functions at both ends. The function is convex. So if we integrate the area below, we get something less. So this is larger or equal than 1 over the trace of exponential minus h. And when we, I mean, the integral from 0 to 1, f of s ds. And this integration, this is just the Duhamel two-point function. So this is AA. So we get an inequality which relates the usual average using the Duhamel two-point function. Now, what we have is an upper bound for this thing, which we would say, I mean, this is smaller than something, and we would like to get an upper bound for this. The inequality goes in the wrong direction. It had to be tried. So then it's not going to work, and one needs something more evolved than this. But it's good to know that there is this relation here. We are actually going to use it in the next hour. Maybe another remark which is worth doing is that from the Cauchy-Schwarz inequality for the Duhamel inner product, we get the following. So if you take the inner product between A and the commutator between B and H, and take this to the square. So this is less or equal. So AA and BH. So let's write this. AA. And then you get also commutator BH. Commutator BH. And then one gets something interesting by just playing around with identities. So actually, also with inequalities. So this is less or equal than this 1/2 A star A plus AA star. This is what we just checked here. Now there is something which I am not explaining why, but the inner product between A and the commutator with H has some explicit expressions. So this turns out to be equal to the expectations of B with A star. I mean, the commutator of B and A star takes the expectation. So we still have this to the square because of that. With identities. So this turns out to be equal to B and then a double commutator. So BH, and we still commute it with H. And now we have a Duhamel inner product between B and the commutator with H. which is also, this is also given by the same formula as for here, as the double commutator BH B star. And so when you look at this, so this is less than this thing times this, and you recognize a famous inequality. And this is indeed so this is this inequality which is important for the Mermin-Wagner theorem for the early versions. So it comes straight out of basically all this little algebra here. So I felt like it was a nice remark to do. We're not going to use it here. Instead, let me state now Falk-Bruch inequality, which is this essential piece in the proof of Dyson-Lipps-Simon. So lemma 3.5, Falk-Bruch, which was taken, and it is as follows. So 2, and then you take this A star A plus A star, you divide by A star and the commutator of H with A, which turns out to be positive because it's also, I mean, this thing, this expectation is pretty much this shape over here. So for the same, with the same identities, you can write it like that, and this expression over here is obviously positive. So this turns out to be less or equals than some function phi, which is increasing, of 4 AA over the same object over here. And what is this function phi? Well, it's a bit complicated. Phi of S equals square root of S, the Koch, 1 over square root of S. And let me point out that this is increasing, but this is also less or equals than square root of S plus S. It's not too hard to check. So maybe it's good to draw it. So we have S, phi of S, and the function behaves like that. Over here, it's like the square root of S, and over here, it's like S plus. This can be easily checked. So what's the thing? I mean, the point is that one wants to have an inequality relating this and this, but in the other direction. And so in particular, what one wants to say is that if the Duhamel two-point function is small, then this should be small. And here it does it because if this is small, then you are in this region over here, and indeed the left side has to be small. But there is some price to pay. I mean, you have a square root, and you also have this double commutator over here, which will have to be estimated. So then one gets the infrared bound for the usual correlation function. So I'm going to finish about in time. And which is that if you take S0 as x in the direction 3, so this is the usual correlation function. It's for a transform at k. And then this is less or equal. Using all these things, doing the calculations with the double commutator, one gets the following bound. It's less than this epsilon u of k, which we saw before, over epsilon k, the square root of this. It's because of this square root over here, plus this thing over here, which is as before, so it's 1 over 2. So now you have the infrared bound for the usual two-point function. And the trick is really, I mean, the difficult thing is to prove Falk-Bohr estimates. Elliott admitted once that they blackened a lot of papers to get it. They were not aware of Falk-Bohr inequality when they worked on this. So it turns out that the proof is not very hard, but you do have to find the proper way of figuring it out. And then it's Jensen's inequality. But to come up to Jensen takes a little while. Once you have it, you have this inequality over here. So there is one major difference compared to the one before. Certainly not this part. The thing is that before, when beta was getting larger, everything was getting smaller. Here, this also goes to 0 as beta goes to infinity. But here, there is no beta. That's the one major difference. And also, you see why the Lauband in the theorem of Dyson-Lipsimon, I mean, why it has this structure here. So let me just, I have 1 more minute to indeed prove the theorem using all these properties here. This board is going to be enough. So the proof of theorem 3.1, we do something very similar to what we did for the classical case. So 1/3 SS plus 1, it's like the 1/3 we had before. This is like S03, S03. I mean, it's not hard to check. This is like S03 to the square. Because of rotation invariance, it's 1/3 and the sum of all these S0 i's to the square, which is equal to SS plus 1 by the properties of spin operators. So this is true, but now this is the correlation function at x equals 0. This we write using the inverse Fourier transform. It's like 1 over lambda, the sum k in lambda star of S0 Sx 3 Fourier transform at k. And then on the right, we also distinguish the x equals 0 k, sorry, k equals 0 case from the rest. So then what you get is that 1 over lambda, the sum over x in lambda S0 Sx 3. Yes, right? So this by the properties of a Fourier transform, I mean, by the definition, is like 1 over lambda and the S03, Sx3 Fourier transform at 0. And this thing at 0 is like the left side minus the sum over all case not 0. It is 1/3 SS plus 1 minus 1 over lambda, sum over all case different from 0 of S03, Sx3, k. And now you say that this is larger or equal when here you put the infrared bound, the upper bound, and this is exactly what we stated and commented before. So this proves this finishes the proof of this amazing theorem. Any question? Yes. Yes, I'm not sure about the values. They have been calculated numerically. That's definitely not optimal. It depends on the spins, but it's not too bad. I mean, it's probably half or maybe even more. I haven't checked it. Other questions? Yes? Yes? That's right, but it's enough that it's be real for one specific basis. So you can choose the basis where you apply this thing. The thing is that you have this inequality, and I I mean, you have to define what is meant by this A bar. And as far as basis, I don't think you would get the same. But definitely you choose a basis and the inequality works. Yes? I don't think so. I mean, yes. So the answer to your first question is yes. So this is this more abstract the definition of reflection positivity by Froelich, Israel, Lip-Simon. So they have a notion of state, and they say that indeed, I mean, you must have this this operation which works like a reflection, and you need that if you take the expectation of an observable and its reflected part, this has to be larger or equal to 0, and then you get a lot of properties out of that. Otherwise, in terms of subadditivity of entropy, I'm not aware of any link between those two. Yes. Yeah, okay. Let's discuss it later. Other question? I guess everybody is impatient for the break. So, break.